Right, the formulas for the mean, the variance, and the standard deviation. Well, the mean is denoted x bar. That's equal to the sum from I equals 1 to n of x sub I divided by n. The variance, s squared sub x, is equal to the sum from I equals 1 to n of x sub I minus x bar quantity squared divided by n. And the standard deviation is equal to the square root of the variance. By all means, memorize the formulas and how to use them. It makes life a lot harder for yourself if you don't memorize the equations. You need to know them in order to understand the next things that I'm talking about. And we'll get to the next thing, which requires you to know what the mean and the standard deviation are. Any questions about that? Then it says find the variance and standard deviation of these numbers. So to find the variance, we need to take each number, subtract the mean, and square it, and sum that up and divide by n. So the next column over here, I'm going to skip. Simply, I'm going to take x sub I minus the mean and square it. And in this case, the mean was given to you as 10, so we didn't have to find it out. If it wasn't given to you, you would simply add up all the numbers and divide by n to get it, but I saved you some time of adding and dividing by telling it to you. So we take each number, subtract the mean, which is 10, and square it. So 0 minus 10 is negative 10, but negative 10 times negative 10 is 100. And 5 minus 10 is minus 5. Minus 5 squared is positive 25. And then I made it easy for you with a whole lot of 10s. 10 minus 10 is 0, and squared is 0. 15 minus 10 is 5, squared, that's 25. 20 minus 10 is 10, squared, that's 100. So then we need to add them up. So the sum of each x sub I minus the mean squared, we then sum it up from 1 to n. So we're adding 100 plus 25 plus 0 plus 0 plus 0 and so on. That's 250. So the sum of it is 250. And then we divide by n, which was 10. And so the variance was 25. How many got 25 for the variance? Looks like about half. Any questions about how to calculate the variance? First thing you need to do is know the formula. Yes?
I'm a little confused because in my math class, they would say it was n minus 1.
Yes,
So
that's
here, is it just n?
right. So this is the definition of variance. And what they're trying to teach you about is sometimes you don't have all the numbers. So here's a population of numbers, maybe 300 million people in the United States. If you draw a random sample of 10 numbers out of these 300 million, so we draw a sample of just n, and n is equal to 10. And we now calculate the sample mean, and we want to make a guess as to what's the population mean. It turns out the sample mean is an unbiased estimate of the population mean. So that's your best guess, but it's not equal to the population mean. And if you want to then guess what's the variance in the population, you can calculate the variance in the sample, but that's a biased estimate because the mean is actually not equal to the population mean. So it's sort of been chosen conveniently. So, but if you want an unbiased estimate, then you multiply by n over n minus 1 times the variance of the sample to get an unbiased estimate. Then the n drops out with the n that's in the denominator, and you end up with an n minus 1 in the denominator. And so they skip all that, and they sometimes tell you to divide by n minus 1 when you're dealing with a sample and trying to guess what's the variance in the population based on a sample. All right. Now, as n gets large, n over n minus 1 turns out to be close to 1, so it's going to make a big difference. But the actual definition of variance is the average square deviation from the mean. And what they're teaching you about is when you have a sample and you want to estimate, have an unbiased estimate of what's the case in the population, they've got this they've already multiplied by the correction factor, they've canceled out the n's, and they put the n minus 1 in there. So that's what that is. And you'll see that in some of the videos. You'll see the n minus 1 just being tossed in there without explanation of where it comes from. But it's an attempt to get an unbiased estimate of the population variance based on the sample variance. All right? How many have had a stat course, so you've heard this distinction before? So you're using a sample to estimate what's in the population. That's where that n minus 1 is coming from. Yes?
I had someone tell me too that you could find the standard deviation first and then square it. Is that always by just looking at the chart like this one is automatically, you see it's 5 apart from each other?
Well,
and then you can square it.
It isn't that going to be that simple because, for example, what if you had a uniform distribution? So try 0, 5, 10, 15, and 20. Suppose you had those 5 numbers. You'll find that the standard deviation is not going to be 5 in that case. All right, so that formula is, or that algorithm is not always going to work. In this example, it works out. That's just the way it's spaced. But notice I got 6 numbers in here. What if there are only 3 numbers in here? What if there were 100 numbers in here, all 10? That would decrease the variance. And if there's only one of those in there, that would increase the variance. So the variance, even though I might have 0, 5, 10, 15, and 20 as my numbers, the distribution is going to change that variance. Any other questions about that? Okay, so those are all good questions. All right. But that's the actual definition of variance, and you're not going to go far wrong with this formula. Whereas the other one, if I give you a sample of 3, or if I give you a population of 3, you could be way off if you use that n minus 1 formula. And we use small n's in this class. All right. Okay. So that's number 1 and number 2. I think I've got, we haven't done the standard deviation. So the standard deviation is the square root of the variance. So the variance is 25. So the standard deviation is going to be equal to the square root of 25, and that's equal to 5. How many got that? All right, so again, any question about the standard deviation? Now, if you knew the standard deviation, you could square it and get it if somebody else had given that to you. Or if you, once you know the variance, you can get the standard deviation, you just take the square root. But if you didn't already know the variance and you had just the numbers here, it isn't quite as easy as you were hoping to get the standard deviation. All right, Pavlov conditioned his dogs to salivate to a bell. How did he do it? Well, he presented the bell with something that he knew would cause salivation. What causes salivation? Food. So he presented the bell with the food. He presented the bell, followed by the food, and if it's a half second later, or if it comes about the same time, that's optimal for classical conditioning. What was the unconditioned stimulus? Food. What was the conditioned stimulus? The bell. What was the unconditioned response? Salivation. What was the conditioned response? Also salivation. Why do we use 2 different words for the conditioned response and the unconditioned response? Because the amount of salivation to actual food differs from the salivation simply to the bell. It has a little different temperature. It can be distinguished, so we want to keep it distinguished in theory. All right? It has a different temporal onset. It has a little bit different, but it's similar to the unconditioned response. So the conditioned response is similar to the unconditioned response. What's taste aversion? Well, this is described for you in Callett's book, and they referred to it in the video. So if you hadn't read Callett's book before, it was kind of hard to follow that. So I want to go through Garcia conditioning. Garcia conditioning is named after John Garcia, who's now retired professor emeritus at UCLA, and he studied this type of conditioning. The conditioned stimulus is a, can I erase this right here so no more questions about 1 and 2? Or the announcements here, so let me erase right in here. So John Garcia studied conditioning of the following type. The conditioned stimulus is equal to a novel smell and taste. So it's a new food ingredient that the animal hasn't experienced before. And the unconditioned stimulus is a poison that generates nausea and vomiting. So the unconditioned response is nausea in humans and vomiting. So what you do is you present a new food to an animal, and then you inject it, or you mix the poison in with the food so they eat it. The animal throws up, and it's called one-trial conditioning because it doesn't take any repetition. Unlike the bell and the food, one trial is all it takes. The animal will avoid something with that smell. It has practical value if you're trying to save the wolves in Yellowstone. As you know, all the wolves were wiped out of Yellowstone Park, and people said it's kind of bad to have all the wolves gone because the deer are now eating all the trees, and you don't want a deer to eat all the trees and deforest Yellowstone Parks. You have to go in there and kill the deer, but it'd be good to have natural limit on the deer, and also keep the deer population healthy. The weaker, unhealthier ones are eaten by the wolves. The wolves get the ones easiest to catch. So they reintroduced wolves, but the wolves run off the park, and they eat sheep. So the ranchers want to shoot the wolves. Ranchers don't like the wolves eating their sheep. What you can do is you take some sheep meat, you put some poison on there so that the wolf will eat it and throw it up, and then they leave the sheep alone. If the sheep is not good eating, you throw up after you eat sheep. If they were people, that's what they'd say, but we're behaviorists, so we wouldn't say that. But it's one trial conditioning. It's also called one trial or Garcia conditioning. And it's described and including some limitations. Not every stimulus, not every CS will work. It works best if it's a novel smell or a taste. Now in the video, so they applied taste aversion in the video, and they were doing taste aversion, and all of a sudden the rats were dying. And what was the taste aversion? What was the flavor they were going to use? Saccharin flavored water. Now normally, you could take rats and you can give them saccharin flavored water, and they prefer it to regular water, and they live happily ever after. It doesn't bother them at all. But in this study, what did they pair with the saccharin flavored water? They gave them a shot with a poison, and it turned out that this poison, the unconditioned stimulus, generated the nausea and vomiting. I'll just put here as, the unconditioned response 1 was vomiting, and that's why they chose it. But this drug also was an immune suppressant. The unconditioned response 2 is immune suppression. And so they paired saccharin flavored with a drug that produces 2 unconditioned responses. Taste aversion, right? So the animals did not want to drink the saccharin if they were given a choice. So if they were 2 bottles, but they didn't have a choice. They now had to drink the saccharin water. And so what was happening now? They were nauseated and their immune systems were suppressed. That's what killed them. If you have a weak immune system, you can't fight off the germs. Been a lot of stuff in the news lately, right? Germs have been in the news, hospital reports, nosocomial infections have been in the news, a lot of other stuff. Our bar across the street over here burnt down, but it doesn't affect any of you because most of you aren't old enough to be drinking over there anyway. Sports bar, right? You heard about that? Any of you go to El Dorado High? Went to El Dorado High, yeah. So we had a problem over there at El Dorado. Not going to comment on that because all the news reports are going to be revised as to what was it, a murder, was it a suicide, what exactly happened or why. If you hear psychologists commenting on it, they don't know what they're talking about. It's irresponsible for people to speak about it and give opinions about what was happening over there. Basically a person died, but we don't really know why yet, and be totally unscientific for anybody to speculate about that. A lot of things have been happening in the news. We got a visitor here today who's a world traveler, He could be in Belgium drinking the beer there. He could be in southern Italy. He might be in Rio de Janeiro today. He might be in Paris, Tokyo. But he chooses to be here today to hear this lecture. So say hello to Matthew. And I'd also remind me to advise you, during part of your education, one of the opportunities that's open to you is study abroad programs. So when you see the sign saying study abroad, look into that and read the brochure about it. It's a great experience. Traveling is a great thing, great part of your education. Taking foreign languages and learning how to communicate and understand another culture, these are great parts. It's no longer required to have a language requirement, but that language requirement will really pay off in the future to be able to understand another language and understand another culture, which you can get by understanding other languages. And that, of course, helps greatly when you travel. All right, so a lot of things happening in the news, germs in the news. If you have a suppressed immune system, which is what happens in HIV infection that produces AIDS, means that the person has a totally compromised immune system. They die from other things, and that's what was killing the rats in the study. So in that study, the conditioned stimulus was the sweet flavored water, the saccharin flavored water. The unconditioned stimulus was the poison that they were using, which produced the vomiting, but it also produced an immune suppression. And so the conditioned response was the taste aversion and the immune suppression. So let's see, I think I went through so that's what was happening. You were getting a conditioned response of the immune system being suppressed simply by drinking totally innocent saccharin flavored water that had been conditioned to produce the immune suppression as a response. So it shows the psychological effect, basically killing these animals based on experience that they had received one time experience could kill the animals. All right, any questions about that? About Pavlovian, yes.
The wolves, they probably had eaten sheep before,
The wolves?
but you were giving as an example, so is it,
Yeah, it wouldn't
is
be a
it not
novel, it wouldn't work
considered
so well. So
Garcia?
if the wolves have successfully killed and eaten sheep, it wouldn't work on those wolves necessarily. Although it might work partially.
Or would
know.
you need
In
repeated
other words,
variance?
you think about your own experience. If you go to a restaurant 3 times, you order a certain meal, you're okay, but the 4th time you get sick and throw up all night. Are you eager to go back there and order that dish? It might work to less of an effect, but it's optimal. And it also doesn't work so well when the conditioned stimulus is something else besides a novel food. All right? So it should be a novel, it works optimally if it's a novel food, and if it's a food as opposed to a light or a new poster that you put up in the cage with the animal, like a picture or something that you put in there. So other kinds of conditioned stimuli don't work so well. So it seems to be a particular kind of condition. That's why it's got its own name, Garcia conditioning, or the one trial. It's like classical conditioning, but a little different, because it seems to be, it's probably pre-wired in there evolutionarily. Think about it. You know, it's evolutionarily advantageous. You know, the recipe is you eat something you shouldn't have and you throw up, it's poisonous, right? So you learn to avoid it. And so the idea of learning that particular association is probably, through evolution, has been programmed to be a different kind of learning. All right? I mean, it's a little bit different type, although some people like to lump it in with classical conditioning, which sometimes they will argue you can condition an animal, use any stimulus. You saw in the video that Zimbardo is saying you could condition any stimulus to any response you want. This would be an exception to that. It's where the food, it works best with food to taste aversion, at this particular one, as opposed to this idea of equipotentiality of any stimulus response connection. All right. Now I put up the video here, or the overhead of a slide I described to you before. This is a slide from Huff's book, How to Lie with Statistics. Calit reproduces it. When Huff's book is quite old, $2,000 a year salary seemed like a reasonable salary. Calit uses this and talks about them as monthly salaries, so it's $2,000 a month. One of the things that's changed, this was realistic distribution back when he published this back in the 50s. The numbers are off, but the shape of the distribution hasn't changed. It's still positively skewed. One difference is that the boss here he's only earning 45 divided by 2. Now the boss is earning, you know, thousands of times more than the average worker. What percent of the people are above the average? Well, in this case, there are 20 cases. 1, 2, 3, 4, 5 of them are at or above the mean out of 20. So out of 25 cases, 5 of them are above, that's 20%. So much less than half are above the mean. What percent are above the median? The answer to that is always the same, doesn't matter what the distribution is. The median, 50% are above and 50% are below. It doesn't matter if it's positively or negatively skewed. What percent are above the mean? Less than half if it's positively skewed, more than half if it's negatively skewed. All right, so you should learn that about the mean, median, mode, and midpoint. This was the example given by Alan. Now the next idea that we have under statistics is the normal distribution. Here's the, you've already studied this one. We're going to go through how to work with the normal distribution. The next formula for you to learn and memorize is this equation for the standard score of x sub I. So the standard score of x sub I, also called the z-score. So I'll talk about the z-score is given by the equation z sub x sub I is equal to x sub I minus x bar divided by s sub x. So to convert any score into a standard score, you simply take the score, subtract the mean, and divide by the standard deviation. Well, we know that the variance in this case was 25, so our standard deviation was equal to 5. So we can convert these scores into standard scores by subtracting the mean, which was 10, and divided by 5. So in this case, we're just going to take x sub I minus 10 and divide by 5. Why are we going to subtract 10? Because that was the mean. Why are we going to divide by 5? Because that was the standard deviation. So the score was 0. 0 minus 10 is minus 10. Divided by 5 is negative 2. So here's the standard score of a raw score of 0. So these are sometimes called raw scores. You probably heard the expression about cooking the books. Usually that means something crooked has happened in the financial world. But people sort of use this metaphor of cooking the numbers here. So these are the raw scores, and here they've been sort of cooked. So we're going to take the raw score of 0, subtract 10, that's minus 10, divide by 5, that's minus 2. So for example, if the raw score was 0, it's 0 minus 10 divided by 5, that's negative 2. The standard score of 5 would be 5 minus 10, that's minus 5, divided by 5, that's negative 1. 10 minus 10 is 0, divided by 5, that's 0. All these are going to be 0. And the z-scores don't need to be integers. I've just created some numerical examples that are sort of kind to you with the numbers being nice and round. Z-scores typically aren't going to be integers like this. 15 minus 10 is 5, divided by 5, that's positive 1. 20 minus 10 is 10, divided by 5, that's positive 2. The standard scores have certain properties. The mean of the z's is always 0. Doesn't matter if it's positively skewed, negatively skewed, normal distribution, uniform distribution, U-shaped distribution. Doesn't matter what the distribution is, the mean is always 0. The variance of the z is always 1. And that means that the standard deviation of the z-scores is always the square root of 1, which is always also 1. So that's why they're called standard scores, because we don't need to worry about the mean and standard deviation anymore. We know the mean is 0, we know the standard deviation is 1. Another thing they're useful for is converting any normal distribution into the standard normal distribution. And the standard normal distribution has the following distribution, which we're going to memorize. Any question about this? So this is the next item on your list, or actually on the list that you've already memorized. So by all means, memorize this right away. This is the z-score of x sub I, or the standard score of x sub I. You take the score, subtract the mean, divide by the standard deviation. Any question about how to calculate it? So we just took, in this case, we knew the mean, we knew the standard deviation, we just subtracted the mean divided by the standard deviation. Again, these don't have to come out as integers, but in this case they do. Their sum of these numbers is always going to be 0. Some of these, well, I haven't got the standard. Got that unsquared there. Any question about the standard score? So one of the good things that a standard score, a z-score, is good for is converting any distribution into the standard normal distribution. Now here's this distribution of the Scholastic Aptitude Test, which has a mean of 500 and a standard deviation of 100. You might have a question like this. In order to get a certain scholarship or to be admitted to a program, you need to be in the top 16% of the SAT math, let's say. What score do you need if the mean is 500 and the standard deviation 100? Or let's say you want to qualify for NCAA athletics and you need to be not in the bottom 16%, but in the top 84%. What score do you need on the SAT to qualify for NCAA athletics? On the SAT. Or to be given a scholarship at an NCAA approved institution. All right, so here's the standard normal distribution, and this, we're going to basically memorize the areas under the normal curve here, or the proportions under them. My artwork isn't the greatest, but here's the z-score. As a mean of 0. The area between 0 and 1 is 0.34. That means that about 1/3 of the cases fall between 0 and 1 on a standard normal distribution. And it's symmetric, so the area between 0 and 1, even though it doesn't look like it on my drawing, is the same as the area between 0 and 1 is the same as the area between 0 and -1. So we have 0.34 on this side. We have 0.135, 13.5% between 1 and 2. And 2.5% above from +2 to positive infinity, 13.5% here, and 0.025 from -2 to negative infinity. The whole thing adds up to 1, so these are proportions that add up to 1. It's symmetric, so that means all the numbers below 0 add up to 0.5, and all the numbers above 0 add up to 0.5. You could also look at it this way, that the area between -1 and +1 is 0.68. So adding that together, we've got 0.68 of the population. 0.68 is about 66 2/3%, so that's about 2/3. So 2/3 of the scores are equal to the mean plus or minus 1 standard deviation. Or have a z-score between -1 and 1. How can you memorize the areas under the normal curve? Now when you take your stat course, they'll give you a table of the areas under the normal curve and ask you to work out values in between and so on. And one of the tricks is, maybe they pulled this on you already if you've had a stat course, is to give you one chart in the book and then hand out a chart to you free to use during the exam that's different. And these charts come in different forms. Some of them give you the area between 0 and z. So they tell you a table for values of z between 0 and z. Some of the tables give you the area between minus z and z. Some of the tables give you the area to the left, so the cumulative. And it was switched to make sure that you can reason your way through this. And if you don't know how to work with it, if you memorize these landmarks, you won't go wrong. You'll know what the right answer is to a pretty good approximation, so that if you come up with a screwy answer when they give you the wrong table, you realize, oh, they gave you the area from negative infinity to z, instead of the area between 0 and z, and you're off by 0.5, something like that. All right. So the way to memorize this is simply to chant the areas under the normal curve: 0.34, 0.135, 0.025, until you've memorized those areas. So let's do that together. You need a statistics cheerleader. But 0.34, 0.135, 0.025. Everybody ready? Yes, I'm going to ask you to chant. 0.34, 0.135, 0.025. You could do louder than that. 0.34,
0.135, 0.025.
So the area between 0 and 1 is 0.34. Between 1 and 2,
0.135.
From 2 to positive infinity.
0.025.
From negative 2 to negative infinity. From negative 2 to negative 1.
0.135.
From negative 1 to 1.
0.68.
All right, so you're going to memorize the areas under the normal curve and remember them forever, because any normal distribution can be converted to the standard normal distribution, which you now know. So you will memorize this and know it. By this transformation. So when they tell you the mean is 100 and the mean is 500 and standard deviation 100, you can immediately convert it into the standard normal distribution. You've memorized the areas, and you know this equation right here. Here's the trick. You put the mean corresponding to 0. These are the z-scores, and these are the raw scores right here. 500 goes here because that's the mean of the scholastic aptitude test. And 100, add 100 plus 100 takes you up to 1 standard deviation above the mean, or a standard score of plus 1. 500 plus 100 is 600. Add 100, that takes us up to 700. 700 corresponds to a standard score of 2. Subtract 100 and we get to 400. Subtract another 100, takes us down to 300. And that's what he's done for you right here. He's showing you that between 400 and 600 on the scholastic aptitude test, 68% of the population is within 1 standard deviation of the mean in a normal distribution. That's what Cal is trying to teach you here in this part of chapter 2. Right. I've discovered that students don't seem to get this on their own. They need some lecture added to reading through the book. Same goes for Cal's explanation of how to calculate the standard deviation. All right, these are the standard deviation or standard units. 0 corresponds to 500, plus 1 corresponds to 600. Let's just check that with our equation. Our equation is the z-score x sub I minus x bar divided by s sub x. So that's equal to 600 divided by 500 divided by 100. So the z-score of 600 is equal to 100 divided by 100, and that's equal to 1. So if you're 1 standard deviation above the mean, it corresponds to a standard deviation or standard score plus 1. So standard scores are basically how many standard deviations are you above or below the mean. If you're right at the mean, when xi equals x bar, the z-score is 0. If xi is greater than x bar by 1 s sub x, the standard score will be 1, and so on. So we've got this linear transformation converts any distribution into a standard normal distribution. And this should become your friend, so champ 0.34, 0.135, 0.025. And if all you can remember is two of those numbers, you can get the third, because the three of them add up to 0.5, right? So you can get the other one by subtraction. So 0.34, 0.135, draw yourself a little picture. And if you get a z-score that's somewhere in between, you say, okay, it's going to be 0.5 here, and then part of this 0.34, you can come up with a pretty good estimate of what the percentile value of a raw score will be by knowing this much about the normal distribution. All right? Any questions about that? So there'll be a homework assignment for you to do on that. And this will be all the statistics we have up until the midterm, and we'll get some more statistics after the midterm. That will be useful. Any questions about it? Memorize the equation for the z-score and how to use it, how to calculate it, and then how to relate it to the normal distribution. Right? So you'll have some homework assignment in how to calculating z-scores or standard scores. Any questions before we erase this? All right.